So here we have another problem that's going to combine the conservation of momentum and the conservation of energy. We've got these masses here, m1, that moves in with its initial velocity and hits this stationary mass. They bounce apart. m1 moves back at a speed of v1, which we know, didn't write down, so it's v1. Okay, which will cause m2, after being hit, m2 will move forward, of course, right? So I'll call that v2, although we don't know it. And due to that velocity, it'll slide up this incline that comes afterwards, and our job is to find the maximum height that it's going to go up. So clearly we have a collision between 0 and 1, situation 0 and 1 here. And then between 1 and 2, well, we start out with m2 having velocity, and then that energy, that kinetic energy, changes into potential energy, right? It goes from having velocity to having height. So we should be able to do something between situations 0 and 1 using the conservation of momentum, and something between situations 1 and 2 using the conservation of energy. For example, if I were to use the conservation of momentum, I could find v2. Then knowing v2, using the conservation of energy, I should be able to find h. All right, let's get going on that. So the momentum at 1 is equal to the momentum at 0. So the momentum at 0 is going to be m1 v1 initial, that's the momentum of m1, plus, well, m2 v2 initial, but v2 initial is 0, so the m2 does not have any momentum initially. And now, in position 1, well, m1 is moving the other way, so negative, it's moving in the negative direction, so negative m1 v1 plus m2 v2. Oops, low on room there. So we know m1, we know v1, we know m2, we know v1 initial, so v2 is our only unknown in this equation, and we can solve for it. We're going to v2 is equal to, add that over, that, I think. Let's give it a couple steps. So now we know this v2, the speed that mass 2 has because it was hit. All right. Did I mention it's a frictionless surface? It's a frictionless surface. They're impacting along at this flat point. But now, m2 is going to slide along and start going uphill until it slows to a stop, reaching its maximum height. Well, yeah, like I said, at a maximum height, its velocity will be 0, right? All right, so let's do conservation of energy on block m2. We know that the energy it will have in the end there at situation 2 is equal to the energy it had before at 1, plus the work done by non-conservative forces. But it's frictionless, and there's no wind resistance or external forces or anything like that, so no work done by non-conservative forces, as happens frequently, right? So in this problem, we have, in this energy problem, going from situation 1 to situation 2, we clearly have kinetic energies involved, and we also have a change in height, so potential gravitational energy. There are no springs or rubber bands or anything, so there won't be any potential elastic energy. So, kinetic energy 2 plus potential gravitational energy 2 equals kinetic energy 1 plus potential gravitational energy 1. Now, recall that kinetic energy, let's see, jot it down right here. Kinetic energy is 1/2 mv squared, and potential gravitational energy is mgh. But in order to talk about a height h, we have to define what we are calling as the height of 0. And so usually it makes sense just to call the ground the height of 0. There, or in this picture, there. So we're calling this the height that they were at 1. That is our height of 0. So anything, any number that we get, any height relative to, will be relative to that. Which is good because our height that we're looking for is relative to the ground being 0. So if the height that they had in situation 1 was 0, then the 0 there makes for 0 gravitational potential energy. So no gravitational potential energy at 1 because the height at 1 was 0. And it certainly has height in situation 2, but no velocity, right? And if it has no velocity, then it will have no kinetic energy at that point. So what we're looking at is the potential gravitational energy here is equal to the kinetic energy of M2 here. Now I'm only looking at M2, right? It's what I'm interested in at this point. So the potential gravitational energy is M2 times G times H. And the kinetic energy it had was 1/2 M2 V2 squared. We found V2 earlier, so all I need to do is solve this for H. I can divide through by M2, and I get that H is equal to V2 squared over 2G. And if I just plug in my V2 from before, I get that the final answer is that H is equal to, well, let's see, M1 over M2 times V1 initial plus V1 all squared on all over 2G. Okay, so conservation of energy and conservation of momentum, different concepts, but like anything pretty much, problems can be created to put them together. So there you have it.